This gone to the separable, but not the exact, right? The exact is not difficult. At least actually the proof of the formula actually is in the homework, but it is pretty straightforward. Right, so the standard form is pdx pxy dx plus q xy dy equals to 0. And the exact differential means this is something coming out from a function in the textbook, a phi function of x and y, and you can say it's equals to 0 or equals constant. Constant, you can just combine it to the other side and call it phi, your phi. So it doesn't matter, you have a function. Right? And then if this is 0, then d phi of this is 0, right? And d phi as a function of two variables, where d phi is just partial p, partial phi, partial x dx plus partial phi, partial y dy, right? So that equals to 0, right? And compare with that, so you require that p is partial phi, partial x, q is partial phi, partial y, right? If this the equation can be written in this form, then it's exact, or p is given by this partial derivative of a function, and q is the partial derivative of y with respect to the same function, then you have the exact form. Then to check whether this is true, then you just take another derivative. So partial p partial y is square partial y partial x. But then partial derivative is the order is interchangeable. So right, partial x partial y partial y, right? That becomes partial q partial x. You just check whether partial p partial y equals partial p partial x. If that is true, then there is a function phi that so that the p is this partial phi partial x, q is partial phi partial y. And once you have that, this actually is, you can say this is a solution. This is an implicit solution of x between x and y, right? You can, if it's possible, you can solve for y as a function of x. So it's not always possible, but if it's not possible, become an implicit solution, and that's fine. And sometimes it's like that. Okay, so and then the formula is given by 7.10. I mean, you don't actually need a formula. Just to say, I mean, you probably did that before, right? And once you have that, so you have two equations. So once you check that this is true, then you can just use these two equations to solve for phi, solve for this function, the step by step to solve for this. It's like, I mean, this is like the process of proving that formulas, 7.10, equation for 7.10. It's like this is like a differential equation, one-dimensional differential equation of x, right? And so you can say, using this equation, you can just write phi of x and y. This integration of partial phi partial x dx. You're only integrating in x, right? And then this x prime y, and The lower limit actually doesn't matter, but I mean, later on you can just give it a name, and then we set a condition between x and y of this like a boundary condition or initial condition. That depends on how you look at it, right? So that is what you can do by this equation, right? Then this is just 0 x and p. That becomes x y y. Right, and that is not all, because this is a function of two variables, right? But you integrate just one of them, you get the function x. So then there's always an integration constant. Like this a function of y that is not because if you add the function of y only, right? Then partial phi partial x will give you this term, but then we'll kill this term. You still get p out. Right? Right? You take the derivative of x, you get this term, right? You get p out, but then partial f partial x obviously is 0 for this term. So you have an extra function. Usually for 1D integral, you get a constant out, but this is a function of two variables, and you get an extra function of the other variable. That's straightforward, right? And now you can use the other equation to try to solve for y, right? And you do that using space, right? And what you can do is just take the y derivative here, so partial phi partial y is x and y. That will give you q x and y, right? And that what you can do is just do a derivative of partial q partial p x y y. Well, I did it wrong. It's x. This is x pi. I integrate over x pi. Yeah. Okay, x pi y partial y. Now this derivative becomes ordinary derivative y. Okay, so and then now you can use this condition. This condition. Partial p partial y is partial q partial x, right? So this is let's go moving 0 x q pi y x pi y f df dy. Okay. Then you solve for y, then just like the usual case, but first you can integrate that out, because this is ddx, and you integrate over x. So you get q x y minus q x y plus df dy. Right? You see what I'm doing? This is a total derivative, and then you integrate, evaluate the two limits. Right? But then you realize that you can cancel the left-hand side with the first term, right? Then the df dy is just equals to q. Now evaluate x sub 0, your choice of your lower limit, and then y. That you can integrate that, so fy is integrating q x sub 0 y dy to y, or you can say y pi, right? And then supposedly you can have a constant now. because this is just a single variable function. But you can absorb the constant into the lower limit and set the lower limit as y0 as a boundary condition, because you now realize that you add this to the other equation, right? So this, right? Now the formula comes this one: x0 x x prime y x prime plus y sub 0 y 0 x sub 0 y dy, right? And now the idea is this: the x sub 0 and y sub 0 is chosen that if the x sub 0 at x sub 0 evaluate these things, it says phi x sub 0 y sub 0, evaluate x equals to x sub 0, y equals to y sub 0, and this is x sub 0, this is y sub 0. So both integral will be 0. That will be 0. Right? So that gives you a boundary condition that because the original, you have already chosen your function become originally it's like that. So this is what you try to get, and now this is setting the condition that at x sub 0, y will be equal to y sub 0. This is like an initial condition, a boundary condition, right? And so that's how you choose your. And it doesn't have to be. You can choose it the other way. But now you get this phi function by this one. Obviously, if you can, it can each term you can actually integrate to closed form, and the form is nice enough that you can solve for x as a function or y as a function of x or vice versa, right? So that's how you get. But this is a formula 7.10. Is that okay? So can you follow all this? I mean, this is in a way is to derive this 7.110, but I mean, you can use it directly and save your thinking. But if you forget the formula and get confused or like that, like in a closed book exam, you forget about this formula. You don't remember this is x or x sub 0 or whatever. You don't just go through the process that I did. Just do integral, right? Just do direct integral, and then you get the correct. As long as you do it correctly, obviously, just following the rule of doing integral, then you get the answer this way. Like, you don't have to use the formula, but if you have the formula, you can use it. Is that okay? So that's separable. And again, some of you may find it boring because you have seen, probably have solved this kind of equation before, right? Okay, so well, the example for this is straightforward. It's a exact case, but it's non-separable. Obviously, separable means it's also exact. It's quite obvious. If it's separable, then it must be exact, right? Because p is a function of x only, q is a function of y only, then both sides will be 0 and satisfy the same equation, right? So this separable is exact, but exact may not be separable. Okay. So, no, okay, erase all this. Just rewrite the formula, but I mean, it depends on what you want. But this example is dy dx is plus 1 plus y over x 0. Right. And the first thing you do, you can put it in the standard form. It depends on how you want to do it. Like dy plus y over x 0. I mean, you can do it this way, or you multiply x throughout and see that it's still not separable. Like if you multiply x, then you have x here, but then you have x plus y on the other side. If you do that, x, and obviously you don't want to mess up the situation when x equals 0 because it's divided by 0. But for these cases, if you have something that looks singular in your equation, then you just need to be a little careful when you solve the equation. Pay attention to that singular point where your solution can avoid the singularity in the equation and still is a valid solution. So that after you get everything, you double check your equation whether your equation is well behaved at the singular point at of the equation. Okay, so if you do that, is slightly easier. The form. So P is this one. So P is x plus y. Here is x, right? And you check whether this is separable by taking the derivative. So partial P partial y is 1. Right? Partial Q partial x is also 1. So it's separable. Okay, so you can, if you want, you can just plug in the formula. The formula says phi y is integrating x of 0 x e, which is x plus y, 1 plus y, 1, right, and then plus y sub 0, y, and q is just x, but then you evaluate x sub 0. So, you divide. Okay. Just do the integral, which should be straightforward because the result is the first term is x squared over 2. So you x 1/2 x squared minus x0 squared. Right? That's the first term. The second term is y. X of 0. And the second one is also straightforward. Right? And that equals 0. And now you get an equation between x and y and see if that can be solved. It seems you just group the term of y and move everything to the other side and divide it by the coefficient, right? So y is equals to, the coefficient is x plus x sub 0, right? And then move everything to the other side. We have 1/2 0 squared minus x squared. Where I got it wrong. So y has 2 terms. Actually, this cancel. X sub 0, x sub 0, y. So it's just x. Y has 2 terms. This one and that one. Right. X. The other term is plus x 0, y sub 0. Is that right? Did I get it right? Right. Hopefully. Now that right. That may or may not be right. But now the final step, like I said last time, is the most important step is check your solution. So you went through a process like plug in a formula and get the solution. Like, that's fine. But then the most important thing is to check whether that satisfies the original equation, right? And the thing to check is the boundary condition that we chosen that when x is equal to x sub 0, then y sub equals to y sub 0. So you substitute x equal to x sub 0. This term is 0. It's x sub 0, and you cancel the x sub 0 here. You get y sub 0. So that's correct. So boundary condition is correct. Now you can see the boundary condition or initial condition because this formula makes sure that the phi at x sub 0 or y sub 0 is 0, right? Because that's by the construction you write it this way. So at x equals x0, the integral is 0. Then y must equal y sub 0 to make this also 0. Okay. And now the second one is whether you satisfy the differential equation. Well, I mean, you just keep moving it, right? So you can say dy dx. You have the two factor. One is take the derivative of the first factor, which gives you minus 1 over x squared, or you can write it minus y over x, right? Because that's when you multiply by the other factor, it says x. I mean, it says y, just this one. But you divide it by 1 over x and take the minus sign, so minus y over x. And the second one is take the derivative of this. The other term is 1 over x, and derivative of this term is this is 0, and this one will have minus q cancel with this minus x. That will give you minus 1, and so this equals to minus 1 plus 1. And the equation originally is dy dx plus this one equals 0. Okay, so you check that. That's also correct. Right. And finally, just like what I mentioned before, so you see whether that solution is well behaved at a singular point at x equals 0. Seems like it's not well behaved, so you need to, right, because you have the extra x term here, and that doesn't cancel. It depends on what your x0 and y0 are, but then you obviously your solution, you need to avoid the singular point, right? At least for this equation. So as long as you are avoiding that, you can. I mean, you can actually draw this graph and plot this graph. As long as you avoid the x equals 0, that is still a valid solution. And x equals 0 for some choice of x sub 0, y sub 0, that will go up. So your solution has a singularity at the singular point of your equation, which is fine if your range of consideration doesn't include a singularity. Right. So that is fine. All right. Any question? So this case, just this example for this case. Obviously, not every equation is as simple as that.